All right, hey everybody. I wanted to make a quick video. I know I said I would. These are the PDF, there's problems for lecture 12. And so I just wanted to kind of buzz through those really quickly. So what have we got here? Let's do screen right. All right. Okay. Isolate many strains of Saccharomyces cerevisiae. Okay, so one quick thing to remember, think about, we're dealing with eukaryotes here. So that changes the game up a little bit from the lac system, which are prokaryotes primarily, and that'll come up in one of these later questions, but just keep that in mind. Not all the rules are the same when you're dealing with prokaryotic gene regulation and eukaryotic gene regulation. Just keep that in mind. All right, failure to grow in galactose, sole carbon source. Great. Using antibiotic Gal1 protein, you determine that 5 mutants are not producing Gal1. Protein is required from galactose metabolism. Excuse me, I'm sorry. Okay, we got to come up with 5 different mutations that basically are preventing Gal1. Let me make this, let me make that a little bit thicker. Okay, so no Gal1 is what we're looking at. All right, that is the goal. Great. Which of these mutations would specifically affect the expression of Gal1? Which would affect the entire Gal regulation? Oh, right. Well, so this question, and this is one of the reasons why I didn't go into this too much in class. It's all based on, in our discussion last week, it's all based on knowing this Gal regulation system, which is multiple parts. It's like a circuit, actually, and it's studied as a really neat circuit. And this was only covered in the lecture, so make sure you've gone through those lecture notes. It's not in the book. Not in the book. There's concepts in the book, and really, this is just kind of a twist on the lac operon. It's just a little more complex. But the big picture, the take home is these are regulations of regulations and pieces that fit together. Co-activators, co-repressors, inducers, all kinds of stuff. When this is present, this is turned on, and all kinds of stuff like that, right? So there's all these checks and balances. Keep in mind, remember those, like, remember the big picture stuff first. Okay, and if you've gone through the images, I think I have a couple images and I will consult with. Right, so Gal3, where does Gal3 fit in on all this stuff? Well, Gal3 plays a role in helping with the presence of galactose, right? It helps activate Gal4, and Gal4 acts as this like enhancer kind of thing, right? So with glucose around and Gal3, then you can basically add the enhancers, which recruit the polymerase, all this fun stuff. It gets shut on. It's turning on the on switch kind of thing. Without Gal3, remember Gal80 sits on top of Gal4, and then that does not recruit the polymerase and things like that. Okay? It shuts it off. Okay, so Gal3 is one of those things that you could do that would shut this whole thing down. It would shut it all down. A loss of function, right? Remember, there's superfunction for Gal3. That's kind of like a constitutive operator kind of thing. Because remember, Gal3 usually needs that, we'll put galactose. It needs that galactose in there to block Gal80, right? You need that in there to get it to work. But if you block Gal3, well, Gal80 is going to remain, and that is going to be blocking Gal4. I wish these numbers made sense. And that's going to keep everything shut down. Okay, so one mutation that would shut down Gal1. Remember, this whole thing is about galactose metabolism, is you could knock out a loss of function for Gal3. Even with galactose, right? It's kind of like almost that would make it like a super. No, it just wouldn't. It wouldn't have its. It wouldn't be act. It wouldn't. There's really nothing in the lac operon like it. What kind of the cyclic AMP side of things, the activator kind of things with the co-activator, cyclic AMP and CAP, catabolate activating protein. But this is a little bit differently. But you knock out that Gal3 loss of function. That is one way to do it, and it will shut down everything. That would shut it all down, entire regulon or whatever. even with galactose. Okay. What else could we knock out? Well, remember we just said gal 80 was a part of it, so now let's start smaller, right? Gal 3 was a big part. Now, gal 80, well, what if that's not sensitive to gal 3 anymore? Right? So I'm sorry, 8. Look what I'm doing. I'm not thinking here. We just knocked out gal 3. Well, because gal 3, remember, blocks it. It pulls apart the gal 8. But if we make this like super, it blocks the block. Right? There's this old movie in the 90s that's called The Big Hit. It's 10:30 at night. I'm going on tangents. The Big Hit, and it's one of Mark Wahlberg's first movies. Anyways, there's like this trace. Never mind. I'm trace buster, funny thing, whatever. But anyways, gal 3 would inhibit gal 80 normally with the presence of galactose. But what if we block the blocking by mutating gal 80, and that's going to shut this down again. That shuts down gal 3. I'm sorry, it doesn't shut down gal 3, but that would shut down gal 4 all the way, which shuts down everything, knocks it out. Okay, so again, the first mutation, we're talking about 5 mutations. We knock out gal 3, boom, done. We knock out gal 80's sensitivity to gal 3, knocks out the whole thing. Again, boom, 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 boom. We're knocking these things out. Great. Well, what else? Well, now let's think about the lac operon, right? What's the first thing that we check when we're making sure things work? Well, we check that P, that promoter. Well, if you break the promoter, this should probably have been the first thing. We break the promoter of gal 1, broken, done. And that would shut down gal 1 specifically, right? That's a cis-acting thing. The promoters directly influence that gene. You knock out the promoter and it's done. Okay, so that's another mutation you can do in there. You shut down the promoter. Okay, we shut down the thing that helps activate it. We shut down the sensitivity to that activator. We shut down the promoter. What else could we do? Now let's think about the lac operon again. What else could we break? Well, we start with the P, right? Well, what about those Z's and Y's? Oh, when we knock those out, that breaks stuff too. Same game here. What if we actually break gal 1? Oh, we actually mutate. We do some type of something. You get an invalid, a broken product. That'd be shut down too. Again, this parallels right there with the lactose operon. Same kind of idea. You break the promoter, that gene's done. You break that gene, just that gene's done. Awesome. Finally, there's one big, like, super kind of inhibitor to this whole product, and it's a whole nother thing, and that is this MIG-1 part of it all. Right? So you got that whole mess with your gal 4, and then sitting on top of that is your gal 80, unless gal 3 comes in and knocks that off in the presence of glucose and this activator thing. Woohoo, yay. But downstream of that, there's this MIG issue. And it pulls in this protein, I think it's called TUP or something like that. And when these bind together, it's a co-repressor that shuts it all down as it is, right? And that's in the presence of glucose. Wait, why? Does that make sense? Yes, because remember, we want to break down lactose, but if glucose is around, we want to use that glucose first. All these concepts, right? All of these themes come along again. But if we mutate that MIG-1, right? We're basically now, what this is kind of paralleling is the super repressor. Typically, your LAC-I is sensitive to lactose, but if it's super repressor, doesn't care about lactose presence. Same thing here. So MIG-1, if glucose is around, it's kind of a little bit opposite, right? If glucose is not around, so no glucose means MIG-1, it does its thing. It's out of there. Glucose is present. MIG-1 sits down, forms this protein binding this co-receptor. So in this situation, if we make MIG-1 completely independent of glucose, we break that connection there. So if glucose isn't there, it would still bind. Well, then that would shut down the entire regulon as well, because that is like one of the last stops, is the MIG aspect on that. Okay, so summary. what can we do? I'll do it in a different order than I just presented it, right? Summary. Look at that promoter for just the gene, just like we did in lac operon. You break the promoter, just that gene's done. We break just that gene, that thing's done. We break the gal-3, which helps turn on things. We break that, shuts down everything. We break down gal-80s, right? So this is a loss of function, by the way, because there's multiple gal-3. We break down gal-80's sensitivity to this, shuts down everything. And then finally, we break that MIG-1 sensitivity to low glucose level. And that's it. Those are 5 mutations, and you can kind of see how they play along. I know I'm going a little quick, but there you go. All right. Let's see. How do I get out of this? Let's go here. Let's discard that. Okay. His minus yeast strain mating type A is made to a Lu minus strain mating type A alpha that also is broken for gal-3. We just talked about that. But this has got a little star. What's the star mean? Is it broken or is it super? Think about that. Assuming this His minus strain carries a wild type version of the gal gene. Great. So that means, there is a normal gal gene, but there's broken. All right, how do we select for the mating products? Mating products means the hybrids. Well, if we put media with no His, well, then that means A is dead. If we have media that's just no leucine, that means alpha's dead. If we put a media that's both of them in there, well, the only thing that would live is the crosses of the two. And that's what we want to know. So you would do His minus and Lu minus media. It's kind of that simple. Would the gal regulon, sounds like science fiction, be on or off in a media lacking galactose? Okay, well now we're talking about that gal-3 mutation with a little asterisk. Sometimes you see this listed as a gal-3 C mutation. This is a gain of function. Dominant gain of function. Constitutive. It's like an OC. Kind of. Obviously, it doesn't function that way. This is going to pull off gal-80 off of gal-4, even if there's no glucose around. That's what it is. It's constitutively pulling that gal-80 off of the 4. It's going to activate stuff. So, doesn't matter. It is immune to the presence of galactose now, and it's going to constantly be turning this thing on. That is what that gal-3 gain of function is doing. All right. Dude, I'm just going to back out of that. Discard that. Check out number 3. All right. Screen. Sorry, there's a little clunky way. The old screen read on my older phone worked better, but this one's a little... I guess this is progress. Okay. So what's up with this? Based on the information in the figure below, how does the gal-4... There's the gal-4. What would sit on top of that? Gal-80. Oh, unless gal-3 is around with... blah, blah, blah. I'm just helping you guys remember the stuff. Oh, no. Okay. How does it regulate 4 different gal genes at the same time? Well, look at that. It's doing this one. It's doing this one. Right? Here's the genes right here. 3 binding sites, 4 genes. That's pretty efficient. Pretty good stuff. Good job, yeast. But how is this like the lac repressor? Well, okay, well, how does it do these 3? Well, that's kind of simple. It's a binding domain, and it matches. So these are motifs, right? Like Tata box or whatever. It's a binding domain that matches to that. So these proteins are produced in such a concentration that there's enough to sit there. It's fine. That shouldn't be surprising. It acts as an enhancer region of all these things. Activates transcription. Great. So this sits in 3 different places to turn on 4 genes. Well, what about the lac operon? How does that lac repressor control 3 genes? Well, that's easy. Because remember in the very beginning of this, I mentioned eukaryotic versus prokaryotic. Well, in a prokaryote, they have these things called operons. And operons are clusters of genes, right? You got the Z, the Y, and the A. Nobody ever talks about the A, but whatever. Right? Lac Z, lac Y, and lac A. And they've got their promoter, and then their operator. And that is where the repressor sits, lac I. And it controls all three of these. Right? Because it will block the polymerase from sitting down and doing its stuff. It's very simple. One binding site. In this situation, since prokaryotes are using a operon system, those genes they're a cluster. It's like one group, and that's all you need to know. That's how those work. Which is cool stuff, by the way. All right, didn't we just do? I feel like we just talked about this. Whatever. Screen right. Okay. How is the activation of Gal1 prevented in the presence of galactose and glucose? Well, when we talked about the breaking stuff, what did we deal with glucose? Well, that was that MIG1. Right? That is sensitive to glucose. If glucose is hanging around, MIG1 is binding. Typically, right? It sits there, right? If we have glucose up, MIG1 sits down. This is I'm trying to, my brain's not working. I'm trying to remember the cyclic AMP, CAP, which when we do our lac operon questions, they're always assuming there's no glucose because that's where the activator part of it comes in. So this is kind of similar. This is kind of the same idea. If glucose is around, MIG1 is going to be part of this thing to shut it down. Okay, so in the presence of both glucose and galactose, MIG1's shutting the party down. Sequence specific binds to this site. You've got where Gal4 binds, which is the UAS, the upstream activating sequence. And the promoter of the Gal1 gene, it's got this TUP1 thing, acts as a co-repressor, and they sit there. Now, if you mutated this, maybe that would change things. But activation, if glucose and galactose are there, it's shut down because, nope, the signals are saying we got to use that glucose first. So we're going to shut down. Again, what does this whole gal regulon thing do? Products to break down galactose. And if glucose is present, we're going to go after that first. That's why. Think big picture stuff. That's why at the very end of all this stuff, you got this MIG1 that puts the brakes on everything. Glucose is there. Sorry, not going to work. And that's that. I think this is the last one. Oh, look at that. I think so as far as I can go up. All right, well, that's it. Screen right. Okay. Predict and explain the effect on Gal1 transcription in the presence of galactose alone. Okay. So, galactose alone, we know MIG1 doesn't matter, does it? It doesn't matter. But how could this matter? Okay, but we have, it doesn't actually say it. Sorry about that. Oh, but it does say galactose alone. So we're assuming that there is no glucose. Okay, so no glucose around. MIG1 is already not binding. So this won't change anything. So just this by itself, it's no effect. However, you pour some glucose in there, right? Oh, whoopsie, someone spilled some glucose in there. Now it's going to still be on. Now it's still going to work. Okay, so as this question is written, no glucose, A does nothing to you. If glucose is around, well, that final checkpoint, that final stop we've been talking about, that doesn't happen anymore, and things can go on, provided galactose is there, right? Because galactose is needed with the Gal3 to pull off the Gal80 for the Gal4. Yay. Okay. I think I broke everything. Oh no. Oh, I'm like doing screen writes of screen writes. Okay, that's A. Deletion of the Gal4 activation domain. Wow, what's the Gal4? Okay, remember Gal4, it's a homodimer, and that sits down on the UAS, and the activation domain is up here, right? That is where Gal3 kind of plays a role, Gal80 can block it and stuff like that. If it's missing its activation domain, well, it's still going to sit there on the UAS, because this domain, the DNA binding domain, positively charged amino acids, things like that, that's fine, it's going to sit down. But the activation domain, what that is going to do, that's going, hey, come here, bring in the promotion, it's promoting transcription. If that's not there, these things sit down, but it's like doing nothing. It's like you want to put an advertisement up, so you get a signpost, but you forget to put the sign on it. Well, yeah, the signpost still sits in the ground, but you forgot to put a sign saying, hey, come here, buy our stuff, right? So that's what's missing. If you're missing that activation domain, well, that's all you got. Gal4 is doing nothing for you. So who cares, galactose, right? It's not the Gal80 wouldn't even really be sitting there because that binds to that activation domain anyways, but it wouldn't be doing its job, so it might as well not have a galactose present. All right, deletion of the Gal1 promoter. There's our P, right? There's our P minus, shutting it off. If you break that promoter, well, what are you going to do? I mean, that's shut down. That's a done deal. I checked that first. No promoter, no gene. You got to have the polymerase binding. No polymerase, no product. It's that simple. All right, E. Deletion of the Gal3, right? Gal3 helps in the presence of galactose, pulls off that Gal80, but we get rid of Gal3. And, well, that means that's just going to sit there. It's going to sit on Gal4. It's going to prevent activation. Done deal. Shut down. And that's it. So these are basically, this question right here is really like, what do each one of these do? What do they do for us? So remember that stuff. Remember the system. It's tricky to find good images. I was going to try and put one on here. I think there might be one in that lecture slide stuff on it, but just remember what's going on. 80 sitting on 4, 3 pulls it off in the presence of galactose. That'll drive things, but at the very end, that MIG one will block it all at the end. But really just think about what each one of those pieces do. Think about how, if you break them, what they do, right? Remember cis and trans? If you've got 2 copies of this stuff, treat it like a lactose thing. Maybe you've got a functional Gal4 here and a broken Gal4 here. Well, this Gal4 can go over there and fine. Perfectly fine. But let's say you break the structural gene, Gal1 over here. Well, that one's broken. Gal1 over here. Well, that one's okay. What if you make like a super repressor version of Gal80? Again, that's also a transacting factor. That'll go wherever you need. So know which one of these are like binding domains. Know which ones of these are proteins that move around, factors, and then you should be okay. All right, I hope that helped. I know I'm a little bit of a mess right now, but I wanted to get this video out. I don't know how long it just went for. I'm going to post this up on YouTube right now. I'll send out a link, and yeah, good luck on your exam tomorrow, guys.